So, how populations grow. So, what three things are going to affect population growth, guys? Reproduction, yeah, very good. What else? What specifically are going to affect those numbers? Like, you are on the right track there. Birth. Huh?
Death.
Death. What did you say, Zeke? I can't hear you.
Predators.
Okay, so death might fall into like the predators. But yeah, you're right with that. But I'm just saying what's going to affect like the number of people in a certain area. The births, the deaths, and migration.
Population units?
Yes. So the number of births, the number of deaths, and the migration. So the number of individuals coming into an area or exiting an area. Okay, moving on. Types of migration. So there are people immigrating, exiting the area, and then there are people immigrating in, entering the area. So I always think of this, immigrate, exit, they both start with the same. Immigrate, in, they start with the same letters. Okay, move on. Equation for population death. You take the births plus the people immigrating in, and you subtract them by the deaths and the people exiting the area, and you get the population growth of the area, whether it's in an incline or a decline. So if you have a positive number, you have growth. If you have a negative number, you have a decline. Okay, moving on. Exponential growth. This is our J-shaped curve. This is when a population grows at a constant rate, okay? So, this occurs when a population has unlimited resources. So did you all see this J-shaped curve when you were doing your buffalo diagrams? Or buffalo models? Did you see the J-shaped curve start out? So almost all populations are going to start out with that J-shaped curve, okay? This is when they have unlimited resources, so they've got enough resources to go around, all right? So another interesting fact, the spread of the coronavirus had that J-shaped curve at first. Now we're starting to see it have more of what we'll call logistic growth, and now we're going to see a steep decline. So all populations start off with this J curve or exponential growth, and that's when it's growing at a constant rate. Moving on. Eventually, all J-curve populations will encounter a limiting resource or factor, even humans. So eventually we all the J curves or the exponential growths meet a limiting resource, okay? Or a limiting factor. What were some of the limiting factors that we went over in the buffalo population models? What would you say, Zeke? Oh, Nathan, did I didn't hear you? I'm sorry, you've got masks on, huh? Food? Yes, food. Yes, grass. So logistic curves, and always is an S curve. So it starts off as a J curve, it meets a limiting factor, and then it starts to kind of level off. Now will it like level off completely like this? No, that's not realistic. But it'll level off. So logistic curves are S curves. They have the S in them. So that's kind of a way to remember it. Logistic has an S curve. I also think it's not logical to think that a population can continue to grow and grow and grow and be able to, and the environment will be able to support it. So I always like to think, logical, logistic. When a population grows, growth rate stops or slows after a period of exponential growth. This occurs when a population reaches carrying capacity, okay? So eventually all populations are going to reach that carrying capacity. This is your population notes. So the population's PowerPoint. Okay, and so we also talked about carrying capacity yesterday. Carrying capacity is the maximum number of individuals in a population that its environment can support. If we go above that, then and make sure you put carrying capacity above that. So if we go above that, you can actually make sure you put carrying capacity above that. I should have done that. So make sure on these notes you put carrying capacity right above this bullet. That's the maximum number of individual environment can support. Remember yesterday you guys looked at the definition of carrying capacity, and when you did, you saw that if the maximum number of individuals in an environment can support, if we go above that, it could actually degrade the environment. So, can actually degrade the environment or destroy the environment if we go above that carrying capacity. Okay, moving on. Limiting factors. This is a condition that causes the growth of a population to decrease, okay? So population decreases when it encounters a limiting factor. Examples of these are predation, disease, natural disasters, food shortages, things like that. Those are limiting factors. And we'll talk about these limiting factors here in just a minute. moving on. Population density, okay? So a population is the number of individuals in an area, so, or the same species in an area. So there's a population of, you could say, humans on Earth, or you could say humans in, the United States. Population density is the number of individuals in a specific area. So the number of deer in 1 acre, the number of people in Knoxville, the number of students in this classroom. So the density of this classroom could be very different from the density in, like, let's say, the media room. So our density would increase if we moved from the makerspace to the media room. It would be a much denser population in there. Does that make sense? But we understand the side okay. Population density actually has its own limiting factors. So a limiting factor that depends on the population size or density is a density dependent factor. There are factors that depend on that density, okay? Such as competition. So the more, buffalo you have in that area, the more they're going to compete with each other for that food. And now there are herbivores in that area. The more predators that you have, or the denser the prey in the area, the more predators that it can support. Parasitism and disease. So let's just, you could talk about coronavirus here. Do you think that coronavirus spread as rapidly through, let's say, New York City as it did Montana? So we could take probably any city in Montana and compare it to New York City, and the spread of the disease, the population is going to be way denser in New York City, so that spread of that disease ran through that city pretty fast. It was one of the first hit, versus like Montana, who they probably still have cities or towns that haven't had a case of coronavirus. I have to look at that. I know that, well, what's this one? I was going to say Hawaii. I think they've had like 2, maybe on one of the islands. Competition when 2 organisms compete over the same limited resource. So that's when you have competition. Predation, when an organism captures and feeds on another organism, the more prey that's available, the more predators the area can support. So when one organism captures and feeds on another organism, so you guys should know what a predator is. The more prey is available, the more predators the area can support. And we're actually going to explore that. Okay, so parasitism and disease. When a parasite or disease needs close contact to be spread from organism to organism, the more dense the population, the more likely it is that the disease will be spread. Okay? So just like with coronavirus, you need to be within like 6 feet of each other to spread the disease, or so they say. The denser the population, the more easily it's spread. Which is why we cut down our population density while the spread was, the transmission rate was higher in that area. Now that it's declining, we can actually increase our student population density in the school. Does that make sense? Are you just going to tell me that so I'll move on? So some density independent factors that will limit population growth, weather and natural disasters. So a limiting factor that affects the population regardless of the population size. So a hurricane's going to come through and wipe out the town, whether it's 100,000 or 100. It doesn't depend on the population size. It's going to do what it's going to do. Tornadoes, another example. It doesn't matter if it's natural or some small town in Kansas. It's going to come through and do what it's going to do, regardless of that population size. Same thing with weather. Weather cycles aren't dependent on those population sizes. They're going to affect the population regardless of the size. So extreme hot or cold, winter frost, heavy rainfall. Natural disasters like hurricanes, tornadoes, flooding, earthquakes, mudslides, and forest fires. These are going to limit the population's growth regardless of the population size. And there was one thing that did not come up, so I'm going to try to figure out. There was a predator-prey relationship that I wanted to show you, and for some reason it didn't show up. That must have been the older version of my PowerPoint.